Hi, everybody. I just wanted to kind of review what we covered in class today. So, there were a number of topics that we got to. We really had a lot to cover on a Monday, which is going to kind of typically be how these classes go because beginning of the week, fresh start, you've hopefully rested a little bit from the weekend. And so, we really want to dig in deep on Monday and Tuesday as we get through our weeks in physics. So, we began with a little free body diagram review. If you remember, we had the balloon, we had the slow mo guy, he landed. And then he and his brother managed to pop the balloon, and then the water went everywhere. And of course, what we noticed, what we reviewed was the idea that if you throw something in the air, the free body diagram is only the gravity force going down. There's no force of motion. From there, we reviewed free body diagrams, and we actually drew a free body diagram for this particular system here. I'm going to actually review that free body diagram because it's a good thing to know. So we basically had the normal force on the blue block, the weight of the blue block, we had the applied force F, and the rule that we came up with is that if you push something with a force, that force can only act directly on the object it touches. So then we had the free body diagram for the little block. It had its normal force, it had its weight, and the force that literally pushes the red block forward is a force. And we labeled these blocks 1 and 2. And what we said is the force that actually moves the red block is a force on 2 due to 1. And the blue block would move faster, except that block 2 is in the way of it. So we also have a force on block 1 due to block 2 pushing back on it. And just to be clear, these two forces are what we call a Newton's third law pair. If you remember, Newton's third law says if A pushes B, B pushes, I'm going to write it like this. Newton's third law says if 1 pushes 2, 2 pushes back on 1 with equal and opposite force. And we actually carefully labeled these forces in class, and that should be in your notes. Okay. Now, continuing with that idea, we had two more free body diagrams we just wanted to study more clearly. We said that both of these objects, this one still and this one moving at a constant velocity and a friction surface, actually, in fact, have completely identical free body diagrams. What we basically said is the motion is not a force. What we also concluded is, yes, there was a force that got it moving in the first place. But then once we got it moving, we could let that force die off. This led us to the notion of inertia. If you remember, we did a little penny flick game where I just gave you a little index card, and there was a penny on it, and you flicked it across the room. We watched a couple of videos on inertia, and what we finally came up with was this notion of inertia right here. This notion of inertia is identical to the notion of mass in physics. We measure mass in kilograms, and we made sure to distinguish the difference between mass and weight, where weight, or Fg, is the force of gravity, and mass is this inertia idea. The idea that an object at rest will stay at rest, an object that's moving will stay moving in a straight line at a constant speed. And if you ever see an object speed up, slow down, or change direction, there must be a force involved. We watched a little bit of distinguished weight and mass. And then finally, what we ended up doing was applying Newton's laws to the solution of part A and B of this problem right here. So this problem consisted of us drawing a free body diagram and writing down the solution and solving it. I'm not going to run through this one again because there's an example on your practice test, but we basically came up with a technique for solving force problems that looks pretty much like this. You know what? I didn't keep the technique. I didn't actually list out the technique, but we did have a 3-step process, and I just want to write it down right here by the problem. So step 1 in any force problem is you draw a free body diagram, then set up balanced / unbalanced forces in X and Y, and then you solve. So that pretty much summarizes what we did for the first part of today. And then in the afternoon, we discussed the notion of impulse and momentum. So the idea of impulse and momentum. Impulse is defined as force times time. Momentum is defined as m times v. And here's what we basically use impulse and momentum for. What we basically say is that when you see something collide, smash, hit, explode, you have a really big force acting over a really small time, and the effect is that the momentum of the object changes. Now, we of course applied this to the notion of the egg drop. And what we discussed there was when you have an egg hitting concrete and an egg hitting a pillow, when the egg hits concrete, it shatters. I guess this is green eggs. Ha 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 ha. And this is egg yolk. What we discussed was when the egg hits the pillow and stops, the change in momentum is the same for both. That means the impulse is the same, but what makes up the impulse is different. So if we look at J for the smashed egg, yes, that equals J for the pillow landing egg, but there's a little difference. The smashed egg has a huge force that stops it over a very small period of time, whereas the pillow egg has a very little force that cushions it gently to rest over a very long time. From there, we actually built a little egg drop basket, and we got to actually test this notion of impulse in real life by applying various forces to greater and greater. We got to apply greater and greater impulses in order to bring moving eggs to rest. Only one group managed to make 2 meters, and this year nobody got 2.5, but totally understandable. We did the lab in about 40 minutes total, so definitely not an issue.